morning. My name is Everett Litton with WSP Parsons Brinckerhoff, and I'm one member of the UCA of SME-YM Executive Committee, joined by Anthony Bauer of Gall Zeidler, Shannon Goff of McMillan Jacobs Associates, Colin Sessions with Jacobs Engineering, and Demetrio Crisculo with Skanska. Our next UCA of SME-YM webinar will be on January 25th, hosted by Dr. Kapila Petheridge at CDM Smith regarding the feasibility of HCD for various projects. Today we will have Mr. David Smith of WSP Parsons Brinckerhoff, my colleague in New York, who's the New York office lead, and he will be presenting on the East Side Access Project. Thank you.
All right, good afternoon, everyone. This is David. Can you hear me?
Yes, we can. Very well. Thank you.
That's great. And let me just check that you can see my full screen right now. All right.
Perfect.
Now we're working?
Yes.
All right. Fantastic. All right. So thank you for your patience, everyone. I am David Smith from WSP Parsons Brinckerhoff here in New York. Thank you, Everett, for your introduction. And thank you for joining. So what are you going to hear about today? So Eastside Access is a major transportation and construction project, of course, underground here in New York, one of the largest in the country. If you're interested in tunnel boring machines, both hard rock and soft ground, hopefully I've got something interesting to say to you. Drill and blast as well, ground freezing, underpinning, all of those things I will cover. So over the last several years, I've worked on many projects, including the Eurasia Tunnel in Turkey, the First Street Tunnel in Washington, D.C. But by far, most of my time while spent here in New York has been on this Eastside Access project. I spent roughly a decade working on various aspects of it, mainly on the Queens side of the project, which is the soft ground side, but also a few years on the hard rock side. And it's a wonderful project to be involved with, a whole variety of construction techniques and problems. And I've cherry-picked the most interesting, or what I consider to be the most interesting, to share with you today. Let me also thank the MTA Capital Construction Group. They are the client for this project, the owner, and they approved me giving this presentation today. So although they're the owner, the ultimate user of the project will be the Long Island Railroad. And the purpose is to bring trains from the Long Island into Grand Central Terminal on the east side of Manhattan. Currently, Long Island Railroad services coming into Manhattan serve only Penn Station. So this will give them another place to serve passengers for. The project, as I said, is really split between two sides, the hard rock side in Manhattan and the soft side in Queens, separated by the 63rd Street Tunnel, which is a part of the project which was constructed way back in the 1970s, but then the city and the country hit a capital crunch, a financial crunch, and it was put on hold until the late 90s. So let me go through, give you a flavor, if you don't know New York that well, of the kind of areas that we're constructing underneath. So firstly, in Manhattan here, Grand Central Terminal. It's got the iconic waiting room, and we are mining two massive new station caverns right underneath this structure. So clearly settlement and vibration were major considerations here. The tunnel boring machines mine right down Park Avenue, which is the street you can see running up and down the middle of this picture. Then in the distance, you can see a couple of multi-story buildings, the Helmsley building and the MetLife building, used to be called the Pan Am building, and we're mining right underneath those as well. The 63rd Street Tunnel, this is a historical photo from the 1970s. You can see that it's 4 tubes, 2 up, 2 down, and a variety of techniques were used to construct this, but primarily under the East River, it used immersed tube, but that was also cut and cover and drill and blast as well. So the upper tubes have been used since about the late 90s as New York City subway tracks, and east-side access will use the lower two tubes. So part of the project involves retrofitting those. Moving over to Queens, which is really my area of focus. This is a picture looking over Sunnyside Yard, which is a major railroad storage yard for Amtrak and New Jersey Transit. Long Island Railroad also uses this area as part of the Northeast Corridor, and they are developing a storage yard of their own right here. So roughly 40 storage tracks, multiple mainline tracks that the mining machines in Queens mined under. So let's move on back to the Manhattan side of the project, and I'll give you some more details. So at the top right of the screen here, the dashed red lines are the existing 63rd Street tunnel, and the blue lines on the left are the new tunnels which have now been constructed primarily using TBMs with open-face machines, rock bolts, and ribs in the poor ground. We did briefly consider drill and blast, but vibration and production rates were a concern, and we considered using segments, but there's so many bifurcations and caverns that had we put up segments, we'd have had to remove approximately half of those. So in the end, we decided to go traditional, what is now traditional TBM with rock bolts and a cast-in-place lining to follow. So this was one of the two TBMs that we used, and as you've seen, we're mining and constructing a major project under some of the highest properties and highest real estate values and highest paid lawyers in Manhattan and in America. So we really didn't want to be doing major open cut construction right there in Manhattan. So everything on the project, with a few exceptions, is brought in from Queens and taken out from Queens through the existing tunnel. And the TBMs are no exception. So you can see the cutter head was split into 5 sections here, shown by the red lines, such that we could bring the core through the existing tunnel, which wasn't big enough to take the whole TBM shield and cutter head. And then we reassembled it on a small assembly cavern on the Manhattan side. So what then? We wanted, the blue shows you the Robbins TBM, which tunnels that was going to construct, and the red shows you the Selly TBM, the one you just saw a photograph of, which tunnels that was going to construct. At the top of your screen, you see the upper level caverns, and at the bottom you see the lower level tunnels. So each TBM was going to do multiple runs to get maximum use out of that equipment, and to mine the tunnels. So it's a case of mining to the end, pulling the TBM back, relaunching it, and mining it. So we used 2 methods for relaunching the TBM. So the first method was TBM goes through, mining the first tunnel, all the way to the tail tracks at the end of the alignment at 38th Street. Take off the cutter head, pull it back, reassemble the cutter head. We, using a combination of drill and blast and Roadheader, excavate a bifurcation cavern, a Y cavern, push the TBM forward, and mine a new tunnel from that cavern. So here's an example of that. We've got the first tunnel that's already completed on the left-hand side. The TBM has been pulled back. Drill and blast with rock bolts to enlarge the cavern. Then you can see the Roadheader machine on the right starting a starter tunnel. I'll come to that in just a second. If you're not familiar with Roadheaders, or even if you are, here's a picture of what we use, and it's got these rotating picks on the top which just mine away at the rock. On the left, you can see the kind of profile it leaves with the scoring, but it's much smoother than what's left by the drill and blast, which is, of course, quite rough. And then in the other extreme on this picture, in the background, you can see the quite smooth profile left by the TBM. So this is the starter cavern, and on the right-hand side, with a few small ribs in there. So we needed this because if you just put the TBM into the cavern, it's got nothing to grip on to push itself into the ground. So this is a gripper machine, and it works its way forward For example, if you're standing, imagine yourself standing in a pipe set vertically on the ground, wearing trainers, sneakers, and you want to go vertically up the pipe. You push your feet out onto the pipe, you move your hands up, you push your hands out until they've got a grip. You pick your feet up, move up, and you work your way up your pipe like that. TBM's doing the same thing horizontally in the ground. It's re-gripping the rock, pushing forward. One set of grippers relaxes, regrips, and keeps pushing into the rock. So in a big cavern, it's too big to get that regrip. So we need the starter cavern to be able to push out sideways and grip onto the rock. Well, this is all great, but all the time we're building this cavern and the starter tunnel, the TBM is sitting there. The crews have to demobilize, then remobilize. We've got expensive kit lying around. We figured there's got to be a better way. So the first thing we did, we looked at that pillar in the middle. And remember, there's a high horizontal jacking force from the thrusters, from the grippers, pushing into that pillar. That pillar needed to be a minimum thickness such that it wouldn't break under those loads. And before we got down there and seen the rock for ourselves, we estimated it would need to be 8 feet thick. However, the rock was really good quality. It's Manhattan schist with unconfined compressive strengths of up to 20,000 psi, generally a bit less, maybe 16,000 psi, with very little faulting in it. So we figured, well, we can reduce that down to 5 feet. That saves the bifurcation. The cavern doesn't need to be so long, but you still need the starter tunnel. We then said, well, how can we make it even thinner? Why don't we put steel strutting on the original tunnel to take those loads? That was good, but then we said, hey, why don't we just backfill a section of that first tunnel with flowable fill, a low-strength concrete, just temporarily while we push off against it. That was great. We now got that pillar down to 2 feet, and we were all happy with ourselves. We presented it to the contractor, who was Shivoni, and they said, well, if you're going to be using this flow fill, why not go a step further and do something quite special? And this is what we did. So on the screen now in black is the tunnels that have to be constructed, but none of them have been yet. So imagine the first TBM building the first tunnel. Let me redo that. First TBM builds the first tunnel and then comes back. We then fill the entire tunnel up through where the bifurcation cavern would have been with flow fill to basically recreate rock. We then mine the TBM on a different alignment through that flow fill, diverging out into the rock to create a new cavern. And we excavate the flow fill, and lo and behold, we've created a bifurcation without any cavern at all. Now, the rock bolting pattern that we put up has to be designed to support the rock spanning this larger span, but we've suddenly shaved many months off the schedule, and we don't have a production site in the middle of our tunnel which blocks all access from Queens to Grand Central Terminal. So this was a huge cost-saving and time-saving innovation. Before I move on, just look at that sharp point which is left there between the two tunnels, and I'll show that to you on a picture. This is a form going in for the flow fill in the first tunnel. And on the right, you can see the rocks from the foliation, which is nicely presented. Flow fill going into the tunnel section. Flow fill complete. Didn't go all the way to the crown, just enough, just high enough for the grippers to work their way through. This is the tunnel boring machine looking at the cutter head. You can see it diverging from the original alignment where the cameraman is crouching and moving off into the rock. And there you can see another view along the top of the flow fill. And in the middle of the picture, you can see one of the grippers pushing against that flow fill. And the rock bolts, you can see the rock bolt pattern and then the crown. This is an excavator removing the flow fill, and you can start to see that sharp edge that I was talking about. But this is my favorite picture, I think, from the whole presentation. So if you haven't liked it up to this point, then I apologize. But you can see how good the rock is. I mean, it's really good quality. it leaves a knife edge between these two tunnels, which unfortunately won't be visible in the finished condition, but quite impressive what the TBM and the rock together can do. And there's a view looking back the other way. So then, of course, we do have to enlarge this using the road header to make a proper cast-in-place concrete connection. All right, so I mentioned earlier the MetLife building and the Helmsley building. So two new station caverns serving 8 platforms, 8 tracks, is constructed right beneath those 2 high-rise buildings and Grand Central Terminal. This is an isometric view of those 2 caverns shown on the bottom right. We've got 4 diagonal escalator shafts, several vertical elevator shafts, and a whole mezzanine for passenger services, ticketing, shops, etc. at an upper level. So I want to focus for a second on the station caverns. This is what they'll look like in the finished condition, with a mid-level mezzanine with escalators coming from platform level here, and then each of the 2 caverns has 4 platform tracks. So how to construct them? Well, we have a TBM already, and we wanted to get maximum use out of the TBM. Once it's set up and going, it's a very cost-effective way of excavating rock. So we excavated 4 tunnels through each of the station caverns using the TBM. In full disclosure, one of them, we only used it 3 times for schedule reasons, but essentially the first cavern used 4 TBMs like this to excavate as much rock as we can the most efficient way. It then also allowed efficiencies for drill and blasting because it gave relief for the rock to break away into, so it made drill and blasting much easier, like this, and then we just profiled to smooth out the rock using the road header. Did the same on the other side, leaving a pillar in the middle. We took out the pillar, take it down to a certain level. At that point, we put in the concrete arch from the 2 haunches you can see there on each side. We made actually a hole first down into the lower level tunnels before taking down the rock using drill and blast. The hole allowed us to push rock into it for easy removal via conveyor belt back to Queens, and then finished the excavation. So here's some photos. The first tunnel's already been drilled and blasted out with the pillar left in the middle. Now you can see the pillar's gone. You can see that haunch on the right-hand side, which is going to support the roof concrete. We wanted to pour the concrete roof at this stage because if we waited until all the construction were done, we'd need a lot of false work and much more expensive form work to come up to the crown. So by doing it now, we saved on that effort. And we got any concerns about stability of the crown and loose wedges forming out of the way early on. Shotcrete going in, excavating down. And there's the cavern, one of the 2 caverns completely excavated out. You can see a couple of cross passages on either side. And in the far distance, you can just make out the 4 bored tunnels heading out beyond there. And if you look at the top, you can see the cast-in-place crown is already completed on those haunches. This is construction continuing earlier this year with the waterproofing membrane. That's the yellow and the blue shown there. The blue separates the membrane into discrete sections, so if any leakage does occur through the final lining, we know where it's coming from, and we have targeted grout pipes, which you can also see, which allow that particular area of waterproofing to be remediated. And you can see the walls going up with starter bars and so on. So the caverns are coming along very nicely. Quickly now, I want to go through the underpinning required for the escalator shafts. So we're coming up in the middle of Manhattan, underneath the existing Grand Central Terminal, underneath Lexington Avenue and the Helmsley building. There is a forest of existing support columns which we need to come through. You can see many of them there, existing Metro North upper and lower level, Vanderbilt Avenue, we somehow need to thread 4 escalator shafts through that forest of columns. And frankly, there wasn't space, so we had to do a bunch of underpinning. So on the right, you can see conceptually what we're trying to do. You can see 3 columns coming down. We needed a header beam, some new piles on either side with pile caps, and this had to be repeated in a pattern in many, many areas to create work zones underneath to allow those inclined shafts to go in. Here's a plan view. On this one, the blue is the existing columns and the red is the new piles. That's the previously existing lower level of Grand Central with the columns coming down. This is our new pile caps going in. This is our header beams going in. Some temporary false work to support those header beams. And you can see that one of the existing columns being cut out there after we've already jacked the load into those buildings. Well, into those columns, which support, as I said, some very expensive real estate. So this was a tricky and sensitive job on the project and was done very successfully. So where that column's falling over there, we could then remove the rubble, start excavating our way down. Everything on the incline, so we're right under the historic train shed here, so we tended to use chemical splitters for the rock instead of drill and blast. Working our way down with specialized equipment for muck excavation. And once again, waterproofing going in. And there's the near finished condition. And the stage of construction now is we're at mechanical and electrical fit out, so escalators are starting to be delivered, etc. All right, moving across the river from Manhattan to Queens. To the east end of the tunnel that was built in the 1970s, the Northern Boulevard crossing. This was about 100 foot long, 120, and about $100 million was the construction cost for this. So at $1 million a foot, it was one of the most expensive parts of the project, but also one of the most complicated. So the tunnel goes from the flooded shaft you can see in the middle, under the road to the right-hand side. You can also see an elevated subway line above the road. That road is Northern Boulevard, one of the main arterial routes out of Manhattan and out of New York. Underneath that road, immediately beneath, is a subway line, the E train, which goes out to Queens, one of the busiest subway lines in New York. And then under those 3 major transportation links, East Side Access is going perpendicularly in soft ground. By now, the Manhattan Schist has dived down. It's now become a gneiss, and there's glacial till and high groundwater table you can see from this picture here. So the method we did for excavating it was ground freezing. There's the various transportation links I mentioned. So in blue there, you can see an arch of ground freezing, which was put in from one side, one shaft to the other, underneath Northern Boulevard, founded on rock. That had to be threaded through a forest of underpinning for the elevated subway, which needed to be resupported on our structure. And the numbers 1 through 7 represent the different drifts that we constructed the tunnel in, using a sequential excavation method using shotcrete. So there is an image of the frozen ground tubes. You can see how many there are. So we let the chilled brine to about -15 centigrade. We let that circulate for about 10 weeks until the groundwater has frozen and created a continuous canopy through this area to both cut off groundwater and to create some structural strength in the arch. Here are the guys installing the freeze pipes through which the brine is circulated. And there are the first 2 upper level adits being constructed, the drifts. So and I'll zoom in on that upper left drift. There's the frozen ground in the face. So you can see it's not just the arch which was frozen. It ended up being most of the face as well, which gave us nice stability, but did make it rather harder to work. Poking out through the shotcrete there, you can see the lattice girders, which on the left-hand side were part of the permanent arch support, not part of this permanent strength. We then had a cast-in-place liner, but I'm comparing it to the shotcrete and ribs on the right, which are excavated during the subsequent drifts. So in the distance, you can see the middle drift is not complete, but the side drifts are complete. You can see some of our temporary underpinning piles coming through the excavation. And if I move on to the next slide, you can see the waterproofing coming through there, similar to Manhattan, with the underpinning still supporting that subway temporarily. Once the permanent liner is in, we can cut those off. So there, permanent liner in, ready to cut off and re-support the underpinning on the permanent liner. And there is the finished structure. All right, next up, the Queensboro tunnels. Again, still in soft ground, the glacial till below the groundwater table. This is the part that I was mainly focused on, and these were a very successful part of the project, completed a few years ago. The contractor was Granite, Trailer Brothers, and a Frontier Kemper joint venture. So first of all, there's a big, instead of an underground bifurcation, we did this open cut. Manhattan is off to the left, where 2 tunnels come in under the East River. And through this open cut structure, which becomes a railroad interlocking, 2 tracks go from left to right into 4 tracks. And we engineered it such that there would be 3 tracks up above and 1 down below, the lower one being a non-revenue, a non-passenger yard lead track. One point to note here is on the right-hand side, well, on the far right, you can see the storage tracks for the Amtrak and New Jersey Transit, which are immediately outside the launch wall. So minimizing settlement as we launched the TBM was key. You can also see right across this shaft is a railroad track on the right-hand side where it widens out. We phased the slurry wall construction and rerouted the tracks via shoe fly such that we could build a bridge over this area before excavation started. So here in cross-section through that railroad bridge, which is in white at the top, we excavated down under the bridge to top of rock, then exposing piles that we'd put in to support the bridge as we went. Drill and blast down, partially around the piles and then partially in between, such that we could put in 4 tunnels: the yard lead, Tunnel A, Tunnel D, and Tunnel B/C. So these were constructed using 2 TBMs. Actually, let me run through some of the construction photos. Here is the team excavating under the bridge. Now we're down to rock, and you can see that trench being excavated in the middle. Looking along the trench to where those bored tunnels will get launched from, and you can see the trains running all the time above our excavation. One thing you may have noticed on the earlier view was on the narrow part of this cut and cover, we used struts, and on the wide part, we used tiebacks. That was partly because you don't want to use overly long struts, but also because in this area is where the tunnel boring machines were lowered down and the precast segments were lowered down as well. So we wanted to leave this area as open as we could for the contractor to make it as efficient as possible. Yard lead A, D, and BC is the sequence. So here, again, if you remember that view across Sunnyside Yard at the beginning, here's a rendering of it. With the yard lead tunnel went first with one machine, followed by Tunnel A with the second machine. The first machine was brought back to build Tunnel D, followed by Tunnel BC. Now, that that last tunnel, BC, is coming up right in the middle of the northeast corridor between tracks going eastbound, westbound. And so again, settlement was very much a concern there. And we had very shallow cover, as low as 6 feet above that tunnel BC where we stopped it in the end. So that was required special coordination with the railroads for potential mitigations, and that went very well. We also mined under Northeast Corridor, Sunnyside Yard, loop tracks, several railroad and NYC DOT bridges, vehicular bridges, and numerous buildings. So here's a view along Harold Interlocking, looking back. In the far distance, you can see the Empire State Building. So we're looking back towards Manhattan, and these are the tracks and catenary systems and signal systems we had to mine under. So using slurry machines, we made sure we had active phase control to equalize the pressure to absolutely minimize settlement. In most cases, it was not measurable, but where it was measurable, it was typically a volume loss of no more than 0.5%. Volume loss being, if you imagine the volume of the tunnel and then the volume of the settlement trough at the surface, divide the settlement trough volume by the volume of the tunnel, that is the volume loss. And it was minimal, typically 0. But to know that as we're going along and to give comfort to the railroads, we had hundreds of monitoring points, both in-ground instruments and rail-mounted instruments, which were, many of them were read automatically. Here's one such reflector going on rail. Here's a theodolite, an AMTS, an automated total station, which constantly cycled between dozens of reflectors to give us real-time monitoring of settlement, had there been any. Here are the 2 TBMs, basically identical, set up both for hard rock and for mixed face and soft ground. As you recall from the photo, that lower tunnel was launched from a full face of hard rock, and even the upper level tunnels had a few feet of hard rock in the bottom. So that's why there are disc cutters as well as rippers on here. Not to mention, this is glacial till, with a lot of large, very strong boulders being carried down from the north during the glacial period. A nice little transporter vehicle with numerous tires at the bottom there, a so-called Goldhofer vehicle, delivering the tunnel boring machine to be lowered down into the shaft. On the left, you can see our separation plant. Given that it's a slurry machine, the bentonite slurry in the face of the TBM not only balances ground pressure and groundwater pressure, but also extracts the sand, gravel, silt, pumps it back to this mini factory here where those components of the soil are separated out and dumped here for taking away. Here's the shield being lowered in. The shield fully assembled. Of course, that railroad bridge got in our way, so we had to assemble it back in the distance, there where the sun is on the wall, and push it forward using jacks under the bridge. So again, on that earlier photo, you saw we're launching immediately after we launch, we come under these railroad tracks. And we want to minimize settlement, and this is how we did it. We constructed a cast-in-place concrete chamber within the box, big enough to encapsulate the whole of the shield of the TBM. We also did a limited amount of jet grouting outside that curved end wall. Incidentally, that curved end wall was designed to act as a horizontal arch, so it didn't need either struts or tiebacks. That made it much easier to penetrate with the TBM. The TBM was pushed up into that concrete chamber. The back was sealed off, and then the chamber was filled with pressurized slurry, such that before we'd even penetrated the wall, we'd already equalized the same pressure that we anticipated outside, and then mined the tunnel. So even though we monitored these tracks very carefully, there was no settlement caused by launching the TBMs. Here's one of those launch blocks going in. And incidentally, these were permanent concrete launch blocks. They were designed with certain box outs for future stairways, electrical chases, and so on. So the concrete did double duty to support the structure which goes in the open cut, as well as for launching the TBMs. The white bars with rods in them are for post-tensioning this this concrete box, both vertically and horizontally, to accommodate the thrust forces from the TBM. Those are the 3 upper level chambers. The lower level one didn't need one because we were going into a full face of rock. So there wasn't a soil or groundwater inflow problem to be dealt with, at least none that couldn't be dealt with a conventional rubber seal. Here's a TBM already launched. You can see most of those pipes are for delivering and extracting slurry from the face. And that is tunnel A, well underway there. So precast segments were used to line the tunnel, whereas in Manhattan, I explained the gripper shield. In Queens, you're in soft ground, so you can't grip against the soil. You have to push off against the tunnel liner that's already built using these precast segments. So they're connected on the circle joint, which is the curved one you can see, also known as the circumferential joint, using dowels. And on the radial joint, also known as the longitudinal joint, using straight anchor bolts. You can see there on the circle joint, we also use plywood packers to help distribute forces. Various jobs I've worked on have used plain concrete, i.e. no packer, concrete to concrete interface. Others have used bitumastic material. This used plywood. Frankly, it's mainly contractor preference, I believe. Various contractors have been successful with all methods, so I'd be reluctant to dictate exactly which method they should use. Here are the segments being pulled up within the tunnel boring machine, within the trailing gear. You can see the dowels being inserted. Incidentally, these segments used conventional reinforcement, meaning cages of rebar, rather than fibers, steel fibers. That was because the 4 tunnels were very close together at the beginning, and the shallow tunnels at the end under active railroad loads imposed high bending moments on these segments. So we needed the strength that the conventional rebar allows. Here's the last segment in a ring going in, the key segment. And you can see the thrust rams in the distance and the ram shoe being pulled back in order to push this key segment home. Then after the ring is complete, the TBM pushes forward, maximum extension on all the rams there. And then at the end of the mining cycle, sequentially, the ram pairs can be pulled back to allow one segment to be installed at a time. Of course, all good things must come to an end, including a tunnel. So the tunnel gets to this reception chamber. Given that it's a slurry machine and it requires fluid to extract the material, we were concerned that if we didn't have a lake at the end of it, a flooded shaft, the TBM might lose fluid before it completed excavating. So we created this chamber that the TBM could mine into, and you can see the gantry crane there ready for pulling out the shield. There's another view of it. Northeast corridor is just off to the left. And here's looking down. So we flooded it up to about spring line, i.e. halfway up the machine, just enough to keep the slurry circuits working. Successfully, the TBM came through. We drained the lake we created, brought in the gull hoffer. We created a road that could drive right in here, pull it up using the gantry, lower it down, and drive it back to the shaft to start tunnel number 2. So this was the shield. The trailing gear was much easier. We could pull it back through the tunnel. The shield is, of course, bigger than the precast segmental lining, but the trailing gear is smaller. So we could pull that back directly, sneak it through the open cut structure, push the shield back to the face, slide it across in position for starting the next tunnel. That's a view through one of the completed tunnels. It's actually Tunnel A, taken basically from where the lake was. And that is pretty much it, and I'd welcome your questions. Thank you for your attention.
Thank you, David. That was absolutely fascinating. And at this time, we'd like to accept questions through the chat panel, and the questions will be read to David and will be recorded. David, our first question is, what was TBM boring rate in linear feet per day through the schist?
I didn't catch the last few words, but the linear boring rate in Queens was typically about 50 feet per day. But I believe the maximum day we got about 80 feet. So Trailer Brothers didn't want to be limited on their mining rate by their separation plant. So they'd put a separation plant in there to allow basically 2 tunnel boring machines to go up to about 80 feet a day concurrently, which partly is why it was so big, but also why the TBMs could go so fast. In Manhattan, I don't know offhand what the mining rates were. They were slightly lower, I believe. I'm guessing in the 35 to 50 foot range, but I don't know.
Thank you. The next question is, what is a chemical splitter mentioned during the escalator construction?
All right, so the chemical splitter is, if you imagine an old style postage stamp where you have perforations and you want to split along the line, you drill a series of holes, such as you would for drill and blast, but instead of putting in an explosive, you put in a chemical compound, much like cement, which expands as it's best known is damite, D-A-M-I-T-E, and it's quite a slow process, but it does avoid vibration problems. So you drill the hole pattern that you need, you put the damite or the chemical splitter into it, and then you come back several hours later and you can remove the rubble using mechanical means.
Thank you. The next question is, could you please provide additional details on the pre-pressurized procedure used before the start of tunneling?
Sure. So our first concept was to do a traditional jet grout plug, the length of the TBM plus a couple of rings outside of the shaft. But that would have meant jet grouting through railroad tracks, and jet grouting is a messy business and expensive. So we came up with this concept to create a pressure chamber using reinforced concrete on the inside of the shaft. And it's really just that, it's a pressure chamber. As you saw from the photograph, let me just go back as I'm talking. We created an orifice which was slightly larger than the outside diameter of the shield, right there. And we pushed the tunnel boring machine up into it. Then we put a steel plate on the back such that we could close off the chamber. Of course, the steel plate was heavily reinforced, and that allows us to pressurize the chamber. We had watertight gaskets, hydrotight and conventional gaskets around all the sides, so that pressurized fluid couldn't escape. But then, whereas on a conventional soft ground tunnel boring machine launch, you have a frame that you push against, we decided not to use a conventional triangular frame here. But on the left, you can see the frame is still there, bolted to the back of this concrete block, and you can see the horizontal post-tensioned anchors going in. So the combination of horizontal anchors and vertical anchors and that frame allowed the thrust forces from the TBM to be transferred down into the rock, which immediately was below this area. I hope that explained the answer sufficiently.
I think it did. Next question is, how did we do against budget in the end?
Well, let me answer that in two ways. The Queensport Tunnel contract, I believe, was a $700 million contract, and there are a few changes to it, but essentially no claims, just some negotiated changes, and that was completed essentially on time, on budget. The job overall is running later than originally planned, and in large part because of the delay is at a higher cost than originally planned. But constructing major works in Manhattan is difficult. You see that from the One World Trade Center project and many of the other mega projects here. There's a lot of different forces coming into play, political, financial, commercial, etc. And also East Side Axis, it's almost like orthoscopic surgery, the Manhattan side. Doing everything with keyhole surgery from Queens is a slow process. It's been very successful. Hardly anyone in Manhattan or Metro North Station knows that we're there, but it is taking longer than originally planned. All right.
And the next comment says, this was an amazing project. Is there anything should have been done differently?
Well, you know, if we were designing an iPhone, I'm sure we would be up to iPhone 7 now and incrementally improving how we did things. But as with most of our projects, they are one-offs, and I think what we did was very successful. So having tried to think while I'm with that introduction, I don't think technically we would have done much different. I think our technical solutions worked quite well. I think on the planning and commercial side, what I would have hoped to see, or let me put it another way, on the next mega project, I would like to see more buy-in from the major players from day one, so everyone is committed to delivering a project. That's very hard to achieve. All right, next, please. I don't hear you right now. Do we have another question?
Was offline.
Hello there.
David,
yeah.
Give us just a second. This is Heather with SME. I believe Jackie's audio is offline. Give us just a sec.
That's fine. So, continuing to answer the question about could we have done something different. I mentioned early on about using segments in Queens, and we decided not to do it because about half the linear length would have had to be removed to make way for the Wye Caverns and the station. And then it would have been difficult to drill rock bolts through those segments and then remove the segments. Though it would have had a schedule advantage, I think, in the areas of having tunnels lined up front without having to come back and do them later. So I think we made the right decision, but if we're doing a do-over, I would go back and look at that even more carefully and see what solution we came up with. It's certainly not conventional to do precast concrete in good rock. Sometimes you do it through shear zones, but I wonder, when all is said and done, if it would have been cheaper, quicker to do that.
Thank you, David. The next question, what was the thickness of pillar you had between tunnel and foundations going under Park Avenue?
The overburden thickness, I think it was 60 feet. However, if we look at that profile, we should be able to tell. The caverns were 65 feet high, are 65 feet high. We'll get there in a second. So Metro North, of course, were very concerned about vibrations, and we had monitoring of their tracks, which I didn't show, and monitoring on buildings throughout Manhattan. So it looks like it was a little less than 65 feet, and in areas, selected areas, perhaps more like 40 feet. So I do recall that that was a particular issue in developing the rock bolting pattern. Clearly, some of the rock bolts came quite close to those existing foundations. All right, next question, please.
Next question reads, what type of emergency response and firefighting provisions were made inside the tunnel?
Do we have any more?
David, this is Jackie. I'm back.
You cut off at emergency response.
Okay, it's what type of emergency response and firefighting provisions were made inside the tunnel?
All right. So I wonder is to do with construction or to do with the final condition. So let me address both. During construction, we had sessions with the FDNY, the Fire Department of New York, to explain to them what we were doing and if there was a fire or a rescue event, how the responsibility was divvied up between the contractors and the unions and the FDNY. One thing we did on the Queens side, the distances weren't very great. The longest tunnel was 3,500 feet, and typically more like 2,500. So the escape route, even at the worst case, was not too long, and there were self-rescuers mounted on the tunnel walls once the TBM got beyond a certain distance. On the Manhattan side, one of the key things was to get an access from the surface down into the caverns for both emergency egress and so even though we didn't use that for mucking or material delivery, that vertical access with an elevator was put in pretty quickly, and that elevator was continuously manned during working. In the finished condition, we followed NFPA 130 with the requirements for emergency exits no more than 2,500 foot apart and cross passages no more than 800 feet apart. So those provisions are part of the design. In Queens, that translated to only the longest tunnel, the Yardley Tunnel, having an emergency exit at the midpoint. Even though that was a non-passenger, non-revenue tunnel, we determined that it needed that emergency exit, and it allowed us to put in a ventilation shaft and a signal position so we could get more train throughput. Then similar emergency exits were constructed throughout Manhattan to allow for egress.
Excellent. Thank you, David. That appears to be our last question. I would like to send a message to all of our attendees that you will be receiving an email when the presentation has been rendered. And you can certainly contact David at the email address shown on the screen if you have any further questions of him. David, would you like to share any last comments with us? And we thank you so much for sharing your expertise.
All right. Well, thank you. You're very welcome. Thank you for your attention, everyone. I'll wrap up really quickly. It has been a fascinating project to work on, and I still field questions about it from time to time from folks still working on the project. So thank you to any of those who are still listening, and thank you all. Have a great rest of the day.
Thank you all. This ends today's session.